Okay, Organic Chemistry 2342. We're going to continue on with Chapter 17. So Chapter 17, Part 3, we learned that we can go and do an acyl substitution reaction with nucleophiles. And in the case of ketones and aldehydes, it actually acts as an addition reaction because there are no good leaving groups. In the case of carboxylic acid and carboxylic acid derivatives, it's all about base strength. So the key here is that you can only make less reactive substrates from more reactive substrates unless you trick them. So what we're going to do is we're going to look at converting different carboxylic acids and their derivatives back and forth based on how we can use that nucleophilic acyl substitution reaction to our favor. Okay, so let's move on to this. So the first one we're going to do is we're going to show you how to convert an acid chloride, a carboxylic acid to an acid chloride. You technically can't do that because chloride is a much weaker base than hydroxide, so we're going to have to figure out a way to trick that. We're going to figure out a way to make cyclic anhydrides, as well as making esters, amides, and amides of that are substituted more than once. So let's start with the acid chloride synthesis first. Now we've already done this reaction where we have a carboxylic acid and we use thionyl chloride, or this compound here is our most common one, to create that acid chloride derivative here. We can also do that with phosphorus trichloride or phosphorus pentachloride, and they all form pretty much the same intermediate where the phosphorus or the sulfur is the one that's binding to the oxygen in the carboxylic acid to convert it into a better leaving group. So let's look at what we have going on in the reaction here. So thionyl chloride is this compound right here. You can imagine this is a sulfur carbonyl-based compound with these chlorides here. So it itself would be like a sulfur analog to a carboxylic acid chloride. And so we have attack by the electrons of the carboxylic acid to the partially positive part of the sulfur here, giving us our intermediate compound here, right here, which is our chlorosulfite compound. Once we have our chlorosulfite compound here, this actually becomes a really good leaving group. After we create our chlorosulfite here, we end up creating chloride ion, which then acts as a nucleophile to displace our chlorosulfite. Notice chloride is a poor base, but the chlorosulfate protonated compound is a neutral species and is very, very good leaving group here. In this case, we have the intermediate is where we have the actual addition of the chloride across the carbonyl carbon onto the carbonyl carbon, followed by the pulling in of the electrons from the oxygen and kicking out to give us our neutral species here, which then further decomposes into SO2 and HCl and yields our acid chloride. Note that this is a neutral species, which means it's a weaker base than the chloride we're using as the nucleophile to make our intermediate here. That's the only way it can happen. We can't have hydroxide leave as a leaving group, so we're making it into something else. Once we get to this compound right here, it thermally decomposes to give us SO2 and HCl. Occasionally, we can use a way to remove this HCl, or just the SO2 is typically boiled off as a gas. Okay, so let's talk about what kind of reactions we can do. Now that we have an acid chloride is typically our most reactive carboxylic acid derivative, which means we should make all other derivatives from this compound, okay? So let's take that acid chloride and do some other reactions with it right here. So the first thing we're going to do is, well, let's just react it with another one of our carboxylic acid salts. When we do that, we produce sodium chloride plus an anhydride. So we can get to our carboxylic acid anhydride, and it can be symmetrical or unsymmetrical depending on what the groups are used for these different compounds here. We can also use it to generate an ester from it by using just an alcohol and some sort of base. The base is going to liberate the chlorine from here and the H from the alcohol here to give us our ester functionality. Or we can also use an amine right here, either a primary, secondary, or ammonia as a non-substituted amine to give us our amides, okay? If we have ammonia, we have a primary amine, and then we can have a secondary or tertiary amide based on that. So typically, most of these reactions involve some kind of base right here, and we use pyridine as a base because pyridine is non-nucleophilic. The pyridine itself is not going to attack the acid chloride. It forms a nice stable compound, and then it produces this soluble acid HCl salt, which is then easily removed from the reaction mixture. Okay. So the other thing we can do is we can actually take our acid chloride and either react it with water to create HCl and our carboxylic acid, or base to create our carboxylic acid salt plus our ion here. So we can go from this acid chloride all the way down across the entire set of more stable acid chloride carboxylic acid compounds, and all the way from the acid chloride. Okay. So moving on to other reactions with acid chlorides, let's get a little more specific about the different amides we can do. So if we use ammonia as our nucleophile here, we can create our primary amide. Notice there's only one carbon attached to that nitrogen. That means it's our primary amide. And we typically do that with an excess of the amine of our nucleophile here so that we can create the salt with the HCl right here and take it out of the solution. So that's one way to do it. The other way to do it is to add a non-nucleophilic base like pyridine to the system, and that will also accomplish the same task. Okay, so now let's move on, and instead of having just ammonia, we have a primary amine. If we have a primary amine, that's going to react. So now we have a total of 2 carbons attached to this nitrogen. When we have 2 carbons attached to that nitrogen, that makes it a secondary compound, and the fact that we have the carbonyl makes it a secondary amide. And again, we can make the equivalent of the salt with the HCl here. And if we take a secondary amine and react it to form our tertiary amide here, because now we have a total of 3 carbons. Again, if we took a tertiary amine and reacted it with our acid chloride, nothing would happen. That's not nucleophilic enough to eliminate and produce the acid. So we would form some kind of salt or some other byproduct, but it would not form an amide. So we can do it with ammonia to form a primary amine to form a secondary amide, and a secondary amine to form a tertiary amide. Okay. So now that we have our amides down, let's look at some other anhydrides we can form. Okay. So one of the simplest ways to do an anhydride is to take the acid, carboxylic acid chloride, and pyridine. And pyridine is enough of a base to create this salt here, the pyridinium hydrochloride, and our amide as well. The other way to do it is, instead of having to include a soluble base here, if we've already made the salt out of our carboxylic acid, we can react it with our acid chloride as long as it's soluble to create the insoluble salt and our anhydride here. It's also possible to create an anhydride through dehydration, but this only works if we can form a 5-membered or 6-membered ring, and it'll work directly with heat. If you do not have a 5 or 6-membered ring, what happens is they're not close enough together to give you, there's no stabilization of forming the ring, therefore it doesn't happen. They do not form it in appropriate yields. You might get a little bit, but it doesn't really, it's not a very useful reaction unless you're forming that 5-membered or 6-membered ring. Okay, continuing on with reactions of anhydrides. Now that anhydrides are that one step lower than acid chlorides, that means we can make anything below it. We can make carboxylic acids, esters, and amides out of them. So if we react it with an alcohol, what we'll end up is 1 equivalent of ester plus 1 equivalent of carboxylic acid. Notice it's really useful to use a symmetrical anhydride for these materials because you cannot selectively choose which side it's going to go on. Okay, so we would prefer to use a symmetrical anhydride to give us our ester plus our carboxylic acid that we can separate out. Now, we can also take an amide of some sort, an amine of some sort right here, and turn it into an amide. That'll create either a primary or secondary amide plus a salt of the other material. Remember, we have to remove a proton from that system to create the amide. Therefore, we're going to make some kind of acetate salt of a quaternary ammonium product, unless we add in an excess base. Then again, another couple simple reactions we can do is to go down to carboxylic acids, and we can add either directly water, which will give us 2 equivalents of the carboxylic acid, or we can add base and get 2 equivalents of the carboxylic acid salt. Again, having a symmetrical anhydride here would be a preferred way to do these reactions because we cannot specify which one we would get from it. Okay, so there's also another reaction we can do, and it is called decarbonylation. We can actually remove a carbon off of the end of the chain through usually a thermal decarbonylation. So we lose CO2 and we end up with an unfunctionalized main chain. This happens for very few things without some extra special group here. The most common way to do it is to actually have what we call a beta keto acid. Now, what that means is that we have a group that is, this would be the alpha carbon, and then this is the beta carbon. So it's 2 carbons over from our carboxylic acid. The reason this works is that allows us to make this 6-membered ring, be able to transfer the proton over to give us our enol, which is, if you can think about it, just a tautomer, a resonance structure for our ketone here, where this hydrogen can then be transferred across here, and then this double bond goes up here to give us our ketone. So this is what we call ketone tautomerism, and that's where we can go back and forth. Notice this always creates a methyl ketone because you have this terminal methyl group here that was your alpha carbon. Okay, so this works out really well. So when you have something like the acetyl acetate ion, so when you have the 1 carbon over, that allows you to take these electrons and move them over, remove CO2, and gain back a methyl ketone. Notice that we have a CH3 at the end of the chain here. Okay. Now, in this case, we are losing exactly 1 carbon and 1 carbon only off the chain. Just like when we use cyanide to put a single carbon on the chain and then hydrolyze with the carboxylic acid, we can use this to remove that 1 carbon off the chain if we can form that terminal methyl ketone. Okay, so another carboxylic acid derivative here is one of carbonic acid. So carbonic acid, if we look at that, is just CO2 and water added together right here. And so if we protonate it, it will form this intermediate here, and then we have water kicking out, and we can end up with CO2 and water and some acid right here. Okay, so because this decomposes so readily, we typically don't use it in this form unless it's dissolved in water. So we have an acid chloride derivative of it. And what we have is this compound right here replacing both of those OHs right here and right here. With chlorine, we can create this compound called phosgene. Okay, phosgene was originally used industrially because it's a very small gas. It's very easy to work with. However, it is toxic and was originally used in World War I as a mustard gas. And so most people don't like to use it. What it's used for industrially is to make compounds like urea. They use ammonia and this is used a lot in fertilizers and is also can be made by all sorts of biological systems. You can also react it with alcohols to make what are called carbonates, okay? So if you think about it, this is like an ester on half of it and an ester on the other half, so it's like a diester. And so we call those carbonates. These are used in polymer chemistry. So if you've ever heard of polycarbonate, it's made from that system. It used to be made with phosgene. In the last system we can take, if we act it with 1 equivalent of alcohol and then 1 equivalent of amine, we get what we call a carbamate, or the more common term is called urethane. So if you've ever heard of polyurethane foam, this is the structure, and it's basically a derivative of this diacid chloride from carbonic acid. All right, that is the section for acid chlorides and anhydrides. We're going to move on in chapter 17.5.